We're now starting part 2 of the rectangular coordinate system, and we're really going to be focused on two-dimensional distance. We have that an ordered pair x, y gives the horizontal and vertical position of a point relative to the origin, the point 0, 0, where the x and y axes meet. We're really going to focus on a point, this center point, and this other point, P, which has variable coordinates because it can move around. And if we move that point around so that its distance from the center is constant, what we really have is a set of points called a circle. And inside that circle we can make a right triangle. We have some useful information, namely the slope formula, which involves delta y and delta x, and then the point slope form for the equation of a line. Now very often we write this form instead of the h but with an x1 and instead of the k with a y1. But we can label the points anything that we want, x1, y1, or h, k. We are also going to talk about the midpoint of a line segment, where the midpoint x-coordinate is just the average of the two x values, and the midpoint y-coordinate is just the average of the two y-coordinates. And of course, we find average by adding together and dividing by 2. So let's take a look at question number 14. We are given that the center of a circle is 1, 2, and we have another point on the circle of 4, 6. And first of all, we want to write the equation of that radius line that passes through the points. So we will use the point slope form of a line, which means that we need to come up with the slope and we need to use any point that we know on the line. We will use y minus k equals m times x minus h. Now to calculate the slope, we are going to use the formula or the definition of rise over run, delta y over delta x. Now remember, delta means change, and change is the final minus the initial value. So the final y value is 6 minus the initial y value of 2. And then for the delta x, we have the x final of 4 minus the x initial of 1. That gives us a slope of 4/3. What that really means is we rise 4 and then we run 3 to the right to go from one point on the line to another point on the line. Now we have the slope. We want to come up with any point on the line to write the equation. Well, we know 2 points on the line. We know the red point, 1, 2, which we could use as h, k. And we also have a second point on the line, which we can use to write the line in a second form. So if we use the red point and we substitute 2 for k, 4/3 for m, and 1 for h, this is the equation of that red radius line. Now we could also use the other point, 4, 6, and replace those for h and k. So y minus 6 equals 4/3 times x minus 4. It's the same line with the same slope, just using two different points to represent the equation. So if we go to Desmos and plot those two lines, we should see that they are identical. They lie one on top of the other. And in fact, if we were to expand this equation and write it in slope-intercept form, we would see that y equals 4/3 x plus 2/3. And this form looks different, but it gives us the same line as the other two forms. So what we're seeing is that the slope-intercept form is actually just another variation of the point slope form. We have the slope, and then the point that we have in this particular case is the special point of the y-intercept, namely the point when x is equal to 0. In that case, the y value is the y-intercept of 2/3. So here we have in question 14 a circle with a center given at 1, 2, and we know that one of the points on the circle is 4, 6. The general form for the equation of a circle requires the center and the radius. The equation is x minus h all squared plus y minus k all squared equal to the radius squared. Now in this case, the values of h and k represent the coordinates of the center point. And in this particular problem, the center is located at 1, 2. So we can replace h with 1 and k with 2, and we also can figure out the radius because we see a right triangle here. Now the hypotenuse of the right triangle is the radius, and here our base is 3 and our height is 4. We can calculate delta x and delta y to work those out. So by the Pythagorean theorem, r squared equals 3 squared plus 4 squared tells us that the radius will equal 5. So we know the radius and we know the x and the y coordinates of the center, so we can write the equation of the circle. X minus 1 in brackets squared plus y minus 2 in brackets squared equals 5 squared, which is 25. Let's go to Desmos now just to confirm that graph and the center and the point 4, 6. Here we've typed in the equation x minus 1 all squared plus y minus 2 squared equals 5 squared. And we see that the center is located at 1, 2. Now I've plotted some other information here which allows me to make a slider of this point P. The point was at 4, 6, but I can drag that point around because I have variable x and y coordinates for many points that lie on the circle. We see different right triangles being formed. They're not similar, but they are all right triangles whose base, height, and radius satisfy Pythagorean theorem. Furthermore, we know that each of those right triangles has the same hypotenuse length, namely 5, which is the radius of the circle. So there has to be some kind of relationship between the equation of a circle and the Pythagorean theorem. So let's label the sides here of the right triangle with our typical letters for altitude for the height, B for the base, and C for the hypotenuse opposite the right angle triangle. Let's export the triangle and relabel it so it's not so crowded. And we can write the equation for the Pythagorean theorem, a squared plus b squared equals c squared. Now let's see how the equation of a circle is really just Pythagorean theorem. We can label this point P with variable coordinates x and y because that point can move around the circle. And we have the other point at the end of the line segment, C, but the distance from the center to any point on the circle is a constant radius, so the hypotenuse is constant. So we're going to label the hypotenuse as the radius, but then we have a height, which we can call the change in y, which is y final minus y initial. So we call that y minus k. We also have the base of the triangle, which is a change in x, which is x final minus x initial, or x minus h. And then because the hypotenuse is the radius of the circle, we will label that with r. So now we can make an equation out of Pythagorean theorem, which basically says that the base squared plus the height squared equals the hypotenuse squared. And so we get delta x all squared plus delta y all squared is equal to the radius squared. And now we simply substitute delta x with x minus h, and we get x minus h in brackets squared, plus replacing delta y with y minus k, and then squaring. That is all equal to the radius squared. So this is the equation of a circle where the center is located at h, k, and the radius is called r. It's the same thing that we saw before, just we have different labeling in terms of coordinates at the end of the radius line segment. Now we can see the same thing happening with the distance formula. If we wanted to find the distance from point A to point B along a line, we have often memorized a formula. But when we see this labeling here, we use the base and the height, calling them delta y and delta x. The hypotenuse then is the distance from A to B, and we might label that distance with a subscript from A to B. And then by the Pythagorean theorem, we know that the base squared, which is delta x squared, plus the height squared, or delta y squared, is equal to the hypotenuse squared, which is called distance subscript A to B, and then we square that. Now we do our same calculation for delta x, but this time we have different labeling. Our delta x is going to be x final minus x initial, namely x2 minus x1, and we substitute that into the Pythagorean theorem. Similarly, y final minus y initial looks like y2 minus y1, and that's what we substitute for delta y, and then we square. And our distance from A to B squared is just, again, the hypotenuse squared. Normally, when we want to calculate distance then, we isolate or solve for the distance from A to B, which means that we would take the square root of both sides of the equation. And when we do that, we get that the distance from A to B is the square root of all of the left-hand side. Rather than memorizing this formula, we can understand that it is really just Pythagorean theorem in disguise. Not only are the equation of the circle and the distance formula Pythagorean theorem in disguise, but one-dimensional distance is really a variation of two-dimensional distance, or the Pythagorean theorem. So in this picture, we've got 2 points, A and B, and we are finding the distance from points A to B. So we use the Pythagorean theorem and we simplified the equation until we isolated for distance from A to B. What we really want to know here, though, is what happens if either the height or the width shrinks to 0. If that's the case, our point B stops being higher up than point A and it starts to flatten. So if we were to flatten the line AB, we would have a horizontal line which is in just one dimension. In this case, we are keeping only the width and eliminating the height. This changes our two-dimensional line segment to a one-dimensional line, which means that the slope of the line is decreasing to 0, the angle of inclination is shrinking to 0, and the y2 coordinate is approaching y1. So we can come up with a simplified version of the distance now from point A to point B. We now have that y2 is equal to y1 because our point that was higher than point A, namely point B at x2, y2, is now down in the same horizontal line, so the y-coordinates are both equal to y1. This means that the second term under the square root is 0, and so our delta y is 0 because there is no change in the y-coordinate from point A to point B. We end up getting a square root of something squared, and if we remember from the part 1 video, the square root of x squared does not equal to just x. Instead, the square root of x squared is equal to the absolute value of x. So now we can see that under the square root, we just get the absolute value of x2 minus x1, which is the distance between x2 and x1, and that is the same as the absolute value of x1 minus x2, or the distance between x1 and x2. So in order to come up with a positive distance, we want to take the bigger number minus the smaller number as we go from left to right, and that will work out to be x2 minus x1 because we put x2 on the right. In number 16, we want to calculate the distance between each pair of points, so we can use our distance formula. When we apply this in part A, we notice that the delta x, x2 minus x1, works out to be 0, because we have 3 minus 3, which we then square. So what's happening is that our width has shrunken to 0, and we only have a height, which means that we have a special case of one dimension here. Working this out gives us that the distance is equal to 7. Now, if we had plotted these 2 points, we would have seen points A and B in the same vertical line. And because they're in the same vertical line, we can simply count the number of spaces between the two. We don't really have to worry about how to subtract, because if we use absolute value, we will ignore any negative number. So I'm going to subtract y2 minus 1 and take the absolute value, which ends up giving me the absolute value of negative 7 altogether. But then the absolute value of negative 7 is just 7 spaces. So we have that the distance is 7 by using absolute value instead of the distance formula. In part B, we see that the 2 points don't lie in the same horizontal or vertical line, so we definitely have a two-dimensional distance problem. We could make a right triangle where the height and base are the delta y and the delta x that we calculated earlier, and the hypotenuse is the distance from on the line segment A to B. When we do this, we get our delta x is 10, our delta y is negative 24, and then by the Pythagorean theorem, we can solve for the distance from A to B. In this case, we end up getting that the distance, or the hypotenuse, is 26. In number 17, we are given that the diameter of a circle has the same endpoints that we saw in the previous problem, and the diameter goes right through the center of the circle. To write the equation of the circle, we need the radius, and the diameter was 26, which means that the radius is 13. And we also need to come up with the center, which is the midpoint of this diameter line segment. If you notice here, we can draw some right triangles, a red one and a green one, that are similar. This is actually a really useful concept in coming up with the midpoint. So recall the equation of a circle is just a variation of the Pythagorean theorem theme, and we need to come up with the center coordinates of h, k. The midpoint is really just the average of the x coordinates and the y coordinates for the two endpoints. So h will be the average of the -4 and 6 x-coordinates, and k will be the average by adding together and dividing by 2 of the 2 y-coordinates. Now we can substitute h, k, and r into the equation, and the equation of the circle really just looks like delta x squared plus delta y squared equal to r squared, where we label the right triangle sides from the center to a point on the circumference. Part B asks us to write the equation of the diameter line, so we can take the two endpoints A and B and use their coordinates to come up with the value for slope. The slope is the rise over the run, and we find the rise as the final minus initial y-coordinates divided by the final minus initial x-coordinates. We get a rise of -24, which is really a fall, and we get a run of 10, and when we simplify the slope, we get a slope of -12/5. Now we're going to use the point slope form, and we can use any point that lies on the line in the equation in point slope form. We also have the center point, which is the midpoint of the line segment AB. Now h and k in this equation form represents any point on the line, and I'm going to choose C because it doesn't have any negative coordinates. Substituting the slope and the h and the k gives the equation of the line that goes through points A, B, and also C. Looking at the graph on Desmos, we can really see this delta x squared plus delta y squared equals hypotenuse squared, forming the right triangle using a point on the circle to the center 1, 7. The diameter line goes through A, B, and C, and we can use any of the points, B, C, or A, with the point slope form to see the different equations of the line. I recommend you pause the video and try to recreate these equations and graphs for yourself to make sure that all points work. Question 18 asks us to determine the coordinates of point C if, first of all, C is the midpoint between points A and B. So let's sketch a line segment between the 2 points, and here we can see that we actually have a right triangle. Extending a vertical line down and a horizontal line across gives us the right triangle base, height, and hypotenuse. So when we want to come up with the midpoint, we're really looking at taking half the base and half the height. In other words, we have similar triangles. So our point C is the midpoint of the two endpoints, which means that we are looking at the average of the x and y coordinates from the two endpoints. So starting off with C is equal to the midpoint of A and B, we get XA plus XB divided by 2, which is the midpoint, and then the same, add together and divide by 2 to get the y coordinates. So let's move that out of the way here, and then when we substitute the numbers in, we can work out the midpoint of the two x's and the midpoint of the two y's. Simplifying the calculations gives us that the midpoint is located at -1, 1. And if we look on our quick sketch using Similarity, we see that we had it fairly well approximated. Now we have a slight variation of the next problem because B is now the midpoint of AC. So I'm going to copy paste and see twice as big a right triangle as the AB line segment. And so point C is now at the end point, which means point B is the midpoint. In other words, we can say that point B is going to be the average of the x and y coordinates from points A and C. To get average, we add two quantities together and divide by 2. This case, we know the xb and the xa, but not the xc. Similarly, we know ya and yb, but not yc. So we need to rearrange to solve for the unknown, which is xc in the first equation. So we multiply to clear the fraction, and then in order to isolate xc, we can subtract xa from both sides of the equation. So xc is equal to 2xb minus xa, and we can substitute values for xb, which is 3, and xa, which is -5. When we work that out, we end up getting that xc is equal to 11. And if you take a look in the sketch, point C in red does look like it's 11 over. We can do the same algebra to solve for yc, and when we substitute the values for yb and ya, we end up getting that the y-coordinate for point C is -8, which looks very accurate compared to the graph. In the remainder of the slides, we see some homework questions for the textbook, section 1.1. We also have a summary of the different topics and ideas about 1- and 2-dimensional distance that we've been discussing. And then there are some optional extension problems to help us to understand the deeper concepts that are tying all of these connected ideas or concepts together. So far in this course, we've seen a lot of line segments, and from those line segments or hypotenuses, we can form right triangles. Another concept that we've been dealing with is the similarity of families of right triangles whose hypotenuses lie parallel or in the same line. When we problem solve and we don't know what to do, it's always a good idea to go back to the basic fundamental concepts. This wraps up 1.1 rectangular coordinates, and we'll be able to build on this moving forward in almost all sections in the remainder of the course.